tidy data and data wrangling. So tidy data. Happy families are all alike. Every unhappy family is unhappy in its own way. So this is a quote from Leo Tolstoy. And an amendment of this quote is that tidy data is all alike. Every untidy data set is untidy in its own way. So this is kind of like a way to think about this tidy data. The reason we like tidy data is because it's consistent, it's easy to work with. Getting untidy data into a tidy format can be challenging, but a worthwhile pursuit. So when I say tidy data, what I mean is that each variable forms a column, each observation forms a row, and each type of observational unit forms a table. Characteristics of untidy data, well, it's impossible to basically talk about all of them because really they can be in any kind of format. So focusing on how to get our data that might come in some strange format into this tidy format, I think, is a main goal here. A lot of the data that you're going to work with in this class is going to be in this tidy manner, but I think it's important to sort of understand that what makes that data tidy and that some of the data you might encounter outside of class will be a little bit different. All right, pipes. So where does the name come from? You worked with the pipe a little bit in your lab, and the pipe operator is implemented in a package called magrittr. It's pronounced and then, and this is what it looks like here. This is sort of a play on, there's a Magritte is an artist that has this pipe that says in French, "This is not a pipe," and so that's where this name comes from. Okay, so how does a pipe work? You can think about the following sequence of actions: find key, unlock car, start car, drive to school, park. And you can express this as a set of nested functions in R pseudocode like this. And so in R, when you're dealing with functions, you end up having to read it from the inside out. So the first thing you do is find your keys, and then you start your car, and then you drive to campus, and then you park the car. So this is kind of conventionally how R functions work. Now using pipes, I think, gives a more natural and easy to read structure. So if I were to write this exact same code in R, I would write it like this. I'm going to find my keys, and then I'm going to start my car, and then I'm going to drive to campus, and then I'm going to park. So if these were real R functions, these two chunks of code would do the exact same thing. I just find this second one a little bit easier to read. And so we're going to be using packages and suites of packages that basically make use of this easier to read pipe format. So what about other arguments? So basically what happens is the way that these functions work is it takes this find keys and it sends the output into the first argument of this start car function. And then it takes the output from this kind of combined part, and it pipes it into the first argument of this drive function. And then it takes the output from all three of these, and it puts it in the first argument of the park function. And so sometimes you might want to put something in a different argument. For example, here, I'm going to take the Star Wars data set, and then I'm going to filter it so that species is equal to human. And so what this is doing is it's passing the Star Wars data set into the first argument of the filter function. But then what I want to do is I want to pass this to the LM function. And it turns out the LM function, the first argument is the equation, mass tilde height. And so I don't actually want to pipe this output into the first argument. I want to pass it into the data argument. And so if you want to do that, if you'd like to pass it into a different argument than the first, you can use the dot. And the dot will specify that the location that you'd like the arguments to be passed to. So if I run this, instead of passing the filter data set into the first argument of the LM function, it will pass it into the data argument, which is exactly what I want here. And so you can look at the call here. It's going to say LM. The formula is mass tilde height. And the data is going to be this dot, which is going to be the filter data set from the Star Wars function, or from the Star Wars data frame. All right, so data wrangling. So for a lot of data wrangling, we're going to use functions from the dplyr package. So here's an example. Bike crashes in North Carolina from 2007 to 2014. And so this data set is in the DS box package. And so if I load that package using library DS box, I can find this data by running nc byte crash. And so I can look at all the variable names. This data set has a lot of variables. We can look at them all by running this names function, names nc byte crash. And I can see a detailed description if I use the question mark, do question mark nc byte crash, and that's going to tell me that this is a data frame with 7,467 rows and 66 variables. As I mentioned in the previous lecture, you can view your data using the glimpse function. And so in the environment after loading with data nc byte crash, you can click on the name of the data frame to view it in the data viewer, or you can use glimpse to take a peek. And so this glimpse is going to tell us the number of rows and columns, as well as each of the names of these columns, what type they are, and a peek at the top couple. So we talked about a grammar of graphics before, ggplot, and dplyr is really a grammar of data manipulation. So it's based on the concepts of functions as verbs that manipulate data frames. Some main functions that we can use in dplyr are filter, which picks rows for matching criteria, slice, which picks rows using indices, select, which picks columns by name, pull, which will pull out a column as a vector, arrange, which will reorder the rows, mutate is used to add new variables, distinct will filter out unique rows, sample n or sample frac will randomly sample rows, summarize will reduce variables to values, and there's a lot more than just these, but these are going to be kind of a lot of the main ones that we're going to be using frequently in this class. So dplyr has some certain rules for functions. The first is that the first argument is always a data frame. And this is nice because it allows us to use that pipe really liberally. And the second kind of rule for dplyr functions is that the subsequent arguments always say what to do with that data frame. And dplyr functions always return a data frame, which again makes it really easy to pipe. And they do not modify in place. And so what that means is that you need to save output that you would like to kind of along the way. It's not going to edit the underlying data. So just a quick note, the pipe operator in dplyr functions, this is the pipe operator, and it means that you pipe the output of the previous line of code as the first input of the next line of code. The plus operator in the ggplot2 functions that we talked about, this is used for layering. And so this means you create the plot in layers separated by plus signs. This is kind of confusing sometimes to mix up these two. I certainly have done it several times where I accidentally run ggplot with a pipe and have to remind myself that I use a plus sign. So this is something that maybe expect to get a little caught up on, but with practice, it'll make a lot of sense. Okay, so the first example I'm going to show you is how to filter to select a subset of rows. So here I want to just filter out crashes in Durham County. And so I'm going to take the NC byte crash data, and then I'm going to filter where county is equal. This double equal sign is saying that I want to make sure that county is equal to Durham. And so if you notice, I've got a reduced data set now. Instead of having over 7,000 rows, I just have 340. I have the same number of columns as before, and every county is listed as Durham. You can actually filter for several conditions at once. For example, if I wanted to filter for crashes in Durham County where bikers were between 0 and 5 years old, I can do that. And so I'm going to take that NC byte crash data and I'm going to pipe it to the filter where county is equal to Durham and bike age group is equal to 0 to 5. And so now I end up with just 4 observations in my data set. All of them have county as Durham, and they also have bike age group as 0 to 5. So this gets to these logical operators in R. So the filter function makes a lot of use of these logical operators. So this is a non-exhaustive list of the type of operators that you can use. For example, this symbol is going to be the less than or equal to, greater than or equal to, exactly equal to. This is what we were using in the previous examples. The exclamation point means not, so not equal to. Ampersand means and. The pipe kind of up and down this line here, that means or. Is.na is going to test if something is missing. Not is.na tests if something is not missing. This %in%, that tests if x is in y. If we add an exclamation point to the outside of this, it's going to test if x is not in y. And not x is going to be not x. So these are all, using these operators is going to result in either a true or a false to indicate if the statement is true or false. All right, we can also select. And so select is going to allow us to keep certain variables. So for example, if I filter down to just those 4 observations by filtering where county is equal to Durham and bike age group is between 0 and 5, I can select just 2 variables that I'd like to include in my data set, locality and speed limit. So now I've got a small data frame with just 4 observations and 2 variables based on my filtering and selection. We can also use select to exclude variables, and so we do that with this minus sign. For example, if I wanted to drop the object ID variable, I would do minus object ID in the select function. And we can also select a range of variables, and so this is going to be based on the order that the variables are included in your data frame. And so I'm taking this NC bike crash data, and I'm selecting from city to locality. And so that selects city, county, region, development, and locality because those 5 variables were in that order in this data frame. So this colon here is what indicates that we would like to do that, to select a range of variables. Another function that's commonly used is summarize, and this is used to reduce variables to values. For example, if I wanted to calculate the average crash hour across all of the entire data frame, I can reduce that variable crash hour into a single number summary by taking the mean within the summarize function. So here the average crash hour is 14.7. Often summarize is used in conjunction with group by. And so, for example, this lets you do calculations on groups. And so if I wanted to take the average crash hour by whether or not the crash was a hit and run, I can first group by hit and run and then do my summarize. And so what that's going to do is it's basically going to say, among those that were not a hit and run, the average hour was 14.6. Among those that were a hit and run, the average hour was 15. All right, mutate is used to add new variables. So a very common way to add new variables is with the case when function. So here's an example of that. I want to add a new variable called weather underscore clear, and I'd like this to be a variable that indicates it's yes when the weather is clear and no otherwise. So I can use this case when function, and I can say if weather is equal to clear, then make this variable be yes. Otherwise, make this variable be no. This is an important point. Most often when you define a new variable with mutate, you're also going to want to save the resulting data frame, often by overwriting the original data frame, but you also could call it something new if you'd like. So for example, here, to save this, so what I mean by save is that when I run this NC bike crash again, I would like this weather underscore clear variable to be in it. And so to do that, I need to use this assignment operator and assign it back to that same name. Another way to do this is I can add the assignment operator to the end of the process and use this NC bike crash, assign the name here. Those are going to be equivalent. So you can either assign it at the top or assign it at the bottom. And so when we do this, when we create a new variable, it's always good to check that your new variable worked like you expected. For example, here I can use the count function to make sure that when my weather underscore clear variable is appropriately handling the weather variable. And so here, if I look at my weather clear, this is the variable that I just created. The first 5 observations are no, and the final one is yes. And if I compare that to weather, It's no when it's cloudy, no when it's fog, smog, or smoke, no when it's other, no when it's rain, no when it's snow, sleet, hail, freezing rain, or drizzle, yes when it's clear. So it looks like it worked. Okay, so I want you to go to Canvas and download the NC Bike Crashes application exercise file, and then go back into RStudio, create a new project, and upload this file, and complete these application exercises. And when you're finished, knit that and upload the HTML file back into Canvas. I think this should take you about 10 minutes, maybe a little bit less.